Welcome to Lecture 10, Modern Database Management, Big Data Technologies. This is your Professor Atif Fareed Mohammed. We will be looking into describing why database management extends beyond relational DBs and DWs, databases and data warehouses. List the main NoSQL DBMS categories, understand MongoDB as an example of a NoSQL database, choose between relational and non-relational or NoSQL databases, describe meanings and demands of big data, list and describe components of Hadoop environment, understand the basics of Pig and Hive. These are the programming languages. So let's look into a little bit more depth what big data is and how analytics take advantage of the databases, data warehouses, and big data. Big data refers to the vast volumes of structured and unstructured data that inundates businesses on the day-to-day basis. This data is not only large in size but also complex and difficult to process using traditional data processing techniques. The concept of big data is characterized by the three V's: volumes, velocity, and variety. Technically, there's a fourth V also that is called veracity. Volume pertains to the enormous amount of data generated every second. Velocity refers to the speed at which new data is produced and processed to meet the demands and the challenges that lie in the path of growth and development. And variety points to the different forms of data which can range from text and numbers to more complex data types like images, videos, and audio files. Analytics, on the other hand, involves examining data sets to draw conclusions about information they contain. With the advent of big data, analytics has evolved to incorporate advanced techniques and technologies to process and analyze large data sets more efficiently. This field, often referred to as big data analytics, leverages tools and methods such as machine learning, statistical analysis, and predictive modeling to uncover hidden patterns, unknown correlations, market trends, customer preferences, and other valuable businesses with information or business information. The primary goal of big data analytics is to help organizations make more informed business decisions by enabling analysts, researchers, and business users to make faster and better decisions using data that was previously inaccessible or unusable. By harnessing the power of big data and analytics, companies can gain a competitive edge in their respective industries, optimize operations, reduce costs, and enhance customer service experience. As I just mentioned, the volume, variety, velocity, and veracity. Veracity, traditional data quality methods don't apply. How to judge the data's accuracy and reference. And value is technically the fifth V. Big data is meaningless if it does not provide value towards some meaningful goal. Schema on the read, data lake. Let's look into this with an example each. Schema on read is a concept in data management that has gained prominence with the advent of big data technologies. Unlike traditional data management approaches that enforce a schema on write, where data structure is defined before data is written to a database, schema on the read allows data to be stored in its raw form and only applies a schema when the data is read or queried. This approach provides significant flexibility as it enables the ingestion of large volumes of unstructured and or semi-structured data without the need of upfront data modeling. It is particularly useful in the environment where data sources are diverse and rapidly changing, permitting organizations to defer to decisions on data structure until the point of analysis. One of the primary advantages of schema on read is its agility in handling evolving data requirements. By decoupling data storage from schema definition, organization can quickly adapt to new data types and sources without the overhead of redesigning their database schemas. This flexibility is crucial for big data applications where the ability to process and analyze varied data sets can provide valuable insights and competitive advantages. However, schema on the read also presents challenges, particularly in terms of data governance and quality. Without a predefined schema, ensuring data consistency and integrity can be more difficult, and additional effort may be required during the analysis phase to clean and transform the data into usable format. Despite these challenges, the schema on read approach is widely adapted in modern data architectures, particularly those leveraging data lakes and NoSQL databases. So the data lake is centralized repository designed to store vast amounts of raw data in its native format until it is needed for analysis. Unlike traditional data warehouses, which require data to be structured and schema defined before storage, a data lake allows for the ingestion of structured, semi-structured, and unstructured data without the need for upfront processing. This flexibility makes data lakes particularly well suited for handling the diverse and voluminous data generated by modern applications, including logs, sensor data, social media feeds, and multimedia content. By leveraging scalable storage solutions and advanced analytics tools, organizations can extract valuable insights from their data, enabling more informed decision making and fostering innovation. Data lakes are often built on distributed storage systems such as Hadoop or cloud based platforms, which provide the scalability and cost of efficiency required to manage large scale data environments. Figure 10-1, the example on JSON and XML. The JSON example is products, the number is 1, name is ZoomX, price is 10. Number 2, name is Wheel Z, price is $7.50. Number 3, name is Spring 10, price is $12.75. The XML example comes in the same fashion, however, the metadata is given in a very different shape and format than the JSON or Java server object notation example. Schema on write versus schema on read. The big data approach is schema on write, requirements gathering and structuring, formal data modeling process, database schema, database use based on the predefined schema. Schema on read is collecting large amounts of data with locally defined structures such as JSON, XML, storing the data in the data lake, analyzing the stored data to identify meaningful ways to structure it, structuring and organizing the data during the analysis process. That is traditional database design. Now let's look into NoSQL in more depth. NoSQL databases represent a significant shift from traditional relational database management systems or RDBMS by providing mechanisms for storage and retrieval of data that are modeled in means other than tabular relations used in SQL databases. NoSQL, which stands for not only SQL, encompasses a wide variety of database technologies designed to handle unstructured and semi-structured data. These databases are particularly well suited for large-scale data storage needs real-time web applications, offering horizontal scalability and flexible schemas that can easily adapt to changing data requirements. NoSQL databases are categorized into several types of including document databases, key-value storage, wide column stores, and graph databases, each optimized for specific data models and access patterns. One of the primary advantages of NoSQL databases is their ability to scale out horizontally by distributing data across multiple servers, which makes them an ideal choice for handling big data and high traffic loads. The scalability is crucial for modern applications that require higher availability and low latency, such as social media platforms, online gaming, and IoT systems. Additionally, NoSQL databases often provide high performance and efficient data handling capabilities for large volumes of data thanks to their optimized data models and query mechanism. However, the flexibility and scalability of NoSQL come with trade-offs such as eventual consistency models and limited support for complex transactions, which may not be suitable for all types of applications. Despite their challenges, NoSQL databases have become a cornerstone of modern data architecture, enabling organizations to build robust, scalable, and high performance applications. These are the key value stores and document stores. Let's look into this with one example each. Key value stores are the type of NoSQL database that use a simple key value method to store data, where each item in the database is stored as a unique key paired with its associated value. This model is highly efficient for read and write operations, making it ideal for applications requiring rapid access to large volumes of data. A common example of a key value store is Redis, which is widely used for caching, session management, and real-time analytics due to its in-memory data storage capability that ensures high performance and low latency. For instance, an e-commerce website might use a key value store to manage user sessions, where each session ID acts as a key and the corresponding value contains user-specific data, such as shopping cart contains the login information that allows the website to quickly retrieve and update session data, providing a seamless and responsive user experience. Whereas document stores are a type of NoSQL database designed to store, retrieve, and manage document-oriented information. In a document store, data is encapsulated in documents, typically formatted in JSON, XML, or BSON, which can contain nested structures and are more flexible than the rows and columns found in relational databases. This flexibility allows documents to have varying fields, making it easier to adapt to changes in application requirements. A popular example of a data store is MongoDB, which is widely used for its scalability and ease of integration and modern applications. For instance, a content management system might use a document store to manage articles, where each article is stored as document contains fields such as title, or author, content tags, and comments. This structure allows for efficient querying and retrieval of article data, as well as the ability to easily update individual articles with new information or additional fields as needed. Now let's look into wide column stores and graph-oriented databases in a little bit more depth. Wide column stores are a type of NoSQL database that stores data in columns rather than rows, providing high flexibility and scalability for large-scale data applications. In a wide column store, each row can have a different number of columns, and data is stored in the column family format, where columns are grouped into families based on their related data. This structure allows for efficient data retrieval and storage, particularly for sparse datasets where not all rows contain data for every column. Wide column stores are optimized for querying large volumes of data and are well suited for analytical workloads that require fast access to specific columns or slice of data. One of the most well-known example of a wide column store is Apache Cassandra, which is designed to handle massive amounts of data across many commodity servers, providing high availability with no single point of failure. Wide column stores are particularly effective for applications that require scalable and flexible data models such as time series data, user activity tracking, and content management systems. For example, a white column store could be used to store and analyze time series data from IoT devices, where each device's readings are stored in columns grouped by time intervals. This allows for efficient querying and aggregation of data over specific time ranges, enabling real time analytics and monitoring. The ability of dynamically add columns and scale horizontally makes byte column stores are powerful tool for managing and analyzing large scale distributed data sets. Hope this is helpful. Now let's look into graph oriented databases. Graph oriented databases are designed to store and navigate relationships between data points, making them an ideal choice for applications that require complex relationship mapping and traversal. In a graph oriented database, data is represented as nodes, edges, and properties, where nodes represent entities, edges represent the relationships between entities, and properties provide additional information about both nodes and edges. The structure allows for efficient querying and analysis of relationships, enabling applications to uncover insights that would be difficult to or impossible to discern using traditional relational databases. Graph oriented databases are particularly well suited for use cases such as social networks, recommendation engines, fraud detection, and network topology management. One of the most popular examples of a graph oriented database is Neo4j, which provides a robust and scalable platform for building graph based applications. Graph oriented databases excel at handling interconnected data and can efficiently traverse deep and complex relationship paths, making them an excellent choice for applications that require real time relationships analysis. For example, a social media platform might use a graph oriented database to manage user connections, where each user is represented as a node and friendships or interactions are represented as edges. This allows the platform to quickly retrieve and analyze social connections, enabling features such as friend recommendations, group suggestions, and targeted content delivery. The ability to model and query complex relationships makes graph oriented databases a powerful tool for applications that rely on understanding and leveraging the connections between endpoints. So this is an example of four-part figure illustrating NoSQL databases. So some of the examples, as mentioned earlier in my discussion, are key value stores, document store, white column store, and graphs. The comparison of NoSQL database characteristics. The performance of key value store is high, whereas document store is high, column oriented is high, and graph is variable. Scalability, key value store is high, document store is variable high, column oriented is high, and graph is variable. Flexibility, key value is high, document store is high, whereas column oriented is moderate. Graph is also high. Complexity is key value store none, document store low, column oriented low, and graph is high. Functionality for key value store is variable, whereas document store is variable low, column oriented is minimal, and graph is graph theory that we utilize. So MongoDB, let's look into MongoDB in a little bit more depth. MongoDB is a popular open source NoSQL database that falls under the category of document oriented databases. It is designed to provide high performance, high availability, and easy scalability. MongoDB stores data in flexible JSON-like documents, where fields can vary from document to document and data structure can be changed over time. This flexibility allows developers to store and manage data in a way that closely aligns with the object-oriented nature of modern programming languages, and making it easier to map application objects to database structures. MongoDB's powerful query language aggregation framework and support for ad hoc queries enable efficient data retrieval and analysis, making it a preferred choice for a wide range of applications from small projects to large scale enterprise systems. One of the key features of MongoDB is its horizontal scalability, which is achieved through sharding. Sharding involves distributing data across multiple machines to handle large datasets and high throughput operations. MongoDB also supports replication, which ensures data redundancy and high availability by maintaining multiple copies of data across different servers. This makes MongoDB particularly well suited for applications that require robust data management and fault tolerance. Additionally, MongoDB offers a rich set of features, including indexing, text search, geospatial queries, and support for various storage engines, which further enhances its capability. Its ease of use, flexibility, and scalability have made MongoDB a popular choice for developers and organizations looking to build modern data-driven applications. Sample MongoDB document with relationships looks like as given on the depiction. Now let's look into Hadoop in a little bit more depth. Hadoop is an open source framework designed for distributed storage and processing of large data sets across clusters of computers. It is built to scale up and from single servers to thousands of machines, each offering local computation and storage. Hadoop's core architecture is based on the Hadoop Distributed File System, or HDFS, which provides reliable data storage by breaking down large files onto smaller blocks and distributing them across nodes in a cluster. This distributed storage mechanism ensures data redundancy and fault tolerance, as multiple copies of each block are maintained across different nodes. Hadoop's ability to handle hardware failures and its linear scalability makes it a cornerstone technology for big data processing and analytics. At the heart of Hadoop's data processing capabilities is the MapReduce programming model, which facilitates parallel processing of large data sets. MapReduce works by dividing input into the independent chunks that are processed in parallel by map tasks. The output of these map tasks is then aggregated and processed by reduced tasks to produce the final result. This approach allows Hadoop to efficiently process vast amounts of data by leveraging the combined computational power of the cluster. While MapReduce has been a fundamental part of Hadoop, other processing frameworks like Apache Spark has also been integrated with Hadoop to provide more advanced and flexible data processing capabilities. Hadoop's ecosystem has grown significantly over the years with a wide range of tools and technologies that extend its functionality and make it easier and more accessible to users. Projects like Apache Hive, HBase, and Pig provide higher level of abstractions and interfaces for data querying, storage, and analysis, making it easier to work with Hadoop without deep expertise in distributed systems. Additionally, tools like Apache Zookeeper and Yarn, yet another resource negotiator, enhances Hadoop's capabilities in terms of cluster coordination, resource management, and job scheduling. The versatility and extensibility of the Hadoop ecosystem have made it a popular choice for organizations looking to build scalable and cost-effective big data solutions. So file system, not a DBMS, not relational, breaks data into blocks and distributes them into various computers or nodes throughout the Hadoop cluster, as mentioned earlier. Each cluster consists of a name node, master server, and the data node that are slaves. Overall control through Yarn, as mentioned earlier. No updates or to existing data in files, just appending to files. Move computation to the data, not vice versa. MapReduce and HDFS looks like this. Hadoop is made of MapReduce, as mentioned earlier, engine. It's a MapReduce engine, and the HDFS clusters. We'll talk about each of these next. Note that MapReduce engine includes an overall job tracker to manage activity on the entire cluster in the master server and task trackers. For each slave of the cluster, each slave is a data node and the master is a name node. Now let's look into MapReduce. MapReduce is a programming model of software framework introduced by Google for processing and generating large datasets with a parallel distributed algorithm on a cluster. The model is composed of two main functions, the map function and the reduce function. The map function processes input data and produces a set of intermediate key value pairs. This phase is inherently parallel and it can be executed independently on different chunks of data across multiple nodes in a cluster. The reduce function then takes the output from the map function and combines those intermediate data tuples into a smaller set of tuples. Typically, by aggregating values associated with the same key, this two-step process allows MapReduce to efficiently handle large-scale data processing tasks by leveraging the distributed computing power of a cluster. One of the key advantages of MapReduce is its ability to scale horizontally, making it well suited for processing vast amounts of data across large clusters of commodity hardware. Scalability is achieved through the division of input data into smaller subproblems, which can be processed in parallel by different nodes. MapReduce frameworks such as Apache Hadoop automatically handles the details of data distribution, task scheduling, and fault tolerance, permitting developers to focus on implementing the map and reduce function for their specific applications. This abstraction simplifies the developments of distributed data processing applications and enables efficient utilization of cluster resources. MapReduce has been widely adapted in various domains for large-scale data processing tasks, including data analysis, machine learning, and information retrieval. Its simplicity and scalability have made it a cornerstone technology for big data processing, enabling organizations to extract valuable insights from massive datasets. However, MapReduce is not without its limitations. The model can be efficient for iterative algorithms and real-time processing tasks, as it involves significant disk I/O operation and latency in task scheduling. Uh, Apache Spark, so to address these limitations, alternative processing frameworks such as Apache Spark have been developed to provide more advanced and flexible data processing capabilities. Despite these challenges, MapReduce remains a fundamental concept in the field of big data and distributed computing. And that's how MapReduce looks like. Other Hadoop components, Pig, Hive, and HBase. Let's look into this with one example each. Apache Pig is a high-level platform for creating programs that run on Apache Hadoop. It provides a simple scripting language called Pig Latin, which is used to write data analysis programs that are then translated into MapReduce jobs to execute on a Hadoop cluster. Pig Latin abstracts the complexity of writing MapReduce code, making it easier for developers to focus on data analysis tasks rather than the intricacies of distributed computing. For example, data analysts might use Pig to process log files by writing a script that loads the data, filters out irrelevant entries, groups the data by a specific field such as the user ID, and then calculates aggregated statistics such as the number of requests per user. This script is then executed on the Hadoop cluster where Pig handles the translation or to MapReduce and the distribution of tasks across the cluster nodes. By simplifying the process of writing and executing data analysis programs, Pig enables users to leverage the power of Hadoop for large scale data processing without requiring deep expertise in distributed system programming. Apache Hive, on the other hand, is a data warehouse infrastructure built on top of Hadoop for providing data summarization, query and analysis. Hive facilitates querying and managing large data sets residing in distributed storage using a SQL like language called HiveQL or Hive Query Language. This allows users familiar with SQL to leverage their existing knowledge to interact with data stored in Hadoop without needing to learn complex MapReduce programming. Hive translates HiveQL statements into MapReduce jobs, which are then executed on Hadoop cluster. For example, a data analyst might use Hive to run a query that aggregates sales data stored in HDFS, calculating total sales by region and product category. The query without that would be written in HiveQL, submitted to Hive, and then executed as a series of MapReduce tasks on the Hadoop cluster. One of the key features of Hive is its stability and ability to provide familiar interface for data analysis, making it accessible to the broader range of users, including those who may not have extensive programming experience. Hive supports various data formats and provides tools for data serialization and deserialization, enabling integration with different data sources and formats. Additionally, Hive includes features such as indexing, partitioning, and bucketing, which enhance query performance and efficiency. Hive also supports custom user defined functions or UDFs, permitting users to extend its capability to meet specific requirements by providing a SQL like interface and rich set of features. Hive simplifies the process of querying and analyzing large scale data stored in Hadoop, making it a valuable tool for data warehousing and business intelligence applications. Whereas Apache HBase is a distributed, scalable, and NoSQL database built on top of Hadoop Distributed File Systems or HDFS. It is designed to provide real time write access to large datasets and is modeled after Google's Bigtable. HBase is particularly well suited for applications that require fast random access to large volumes of data, making it a popular choice for use cases such as messaging systems, sensors data storage, and real time analytics. HBase stores data in tables where each row is identified by a unique row key and data within a row is grouped into column families. This structure allows for efficient data storage and retrieval as well as horizontal scalability through the addition of more nodes to the cluster. One of the key features of HBase is its ability to handle sparse datasets where tables can have a large number of columns, but individual rows may only contain data in a small subset of those columns. This flexibility makes HBase an ideal choice for applications with evolving data requirements, as new columns can be added without the need of schema modifications. HBase also supports automatic sharding, which distributes data across the cluster to ensure load balancing and high availability. Additionally, HBase integrates with other Hadoop ecosystem tools such as MapReduce and Apache Spark, enabling advanced data processing and analysis capabilities. For example, a real time analytics application might use HBase to store and retrieve user interaction data, leveraging its fast read write capabilities to provide up to date insights and recommendations. By providing a scalable and flexible data storage solution, HBase enables organizations to build robust and high performance applications for managing and analyzing large scale data sets. This is an example of sample data set for pig and hive examples. This is sample pig script to load data from CSV files. Data1 is equal to load, and then you have given all the thing as, and you're converting that into a table form, and then you dump data1, and that is where your data has been stored now. That's the sample pick script with filter and generate clauses. All right. The sample create table query in Hive. Create table customer, user ID is integer, gender is string, salary is integer, zip is string, age is integer, row format delimited, fields terminated by, and then it's technically pretty much like SQL. Integrated analytics and data science platforms. Some of the vendors are bringing together traditional data warehousing and big data capabilities like HP, HSaveN. Hewlett Packard Technologies has brought that in. Teradata Astra is another. IBM Big Data Platform is also another has brought out. Teradata Astra Discovery looks like this. Teradata Unified Data Architecture Logical View looks like this. That has data insights and actions. Teradata Unified Data Architecture Systems conceptual view looks like this. Hopefully this has given you some decent understanding of big data analytics. See you in the next lecture.